In this video, you will use the assay management capabilities within Aspen hysys to accurately represent a crude oil. You will also be able to effectively use the spreadsheet and case study tools within your process flowsheet. In this example, a recombination of test separator data create a crude oil stream that's mixed with a light gas stream to recreate a source production fluid. This fluid then sent to two stages of separation so that the gas and liquid are separated at two different pressure levels. This video includes the following tasks: specify the assay information, attach the assay, build the flowsheet, add a spreadsheet operation, run a case study. Task 1. Specify the assay management information. The Aspen hysys assay management feature greatly simplifies the specification of properties environment inputs when it is used. In this portion, you will see firsthand how once the assay management option is invoked, hysys will load a suitable component list and create a fluid package. Start a new case. Click on the Petroleum Assays folder in the navigation pane. The assay management option debuted in Aspen hysys version 8.4. Assay management offers many advantages over the Heritage Oil Manager approach. This advantage includes more advanced oil characterization techniques, more options for oil assay data entry, including sulfur content, aromatics by weight, octane number that weren't available with the Oil Manager, the ability to onboard data from internal and external sources, a built-in library of numerous crude oil samples from around the globe, multiple options for manual input of assay data. One of the most convenient advantages of the assay management feature is that it contains its own component list. This component list consists of both data bank and hypothetical components. The hypo component properties are adjusted and modified as you characterize your assay. You will note later in this task that the component list is automatically loaded. Please note that the assay management component lists are loaded within Aspen hysys upon installation. Begin by adding assay data to the assay management environment. This can be done in three different ways: importing from a library of assays, importing data from a compatible assay data source type, manually specifying assay data. In this exercise, you will use the manual data entry approach to provide some assay data. Click the pull-down arrow next to the Add button and select Manually Enter to enter your assay data. Select the assay component Celsius to 850 degrees centigrade. Click OK. A new assay input window will appear. Keep the default name of assay 1. Note that a fluid package titled Basis 1 was assigned as well. Each option allows you to enter information differently. Multi-cut properties default option lets you specify mass, molar, or volumetric cuts of the crude assay sample with user-defined initial and final boiling points. Single stream properties let you define the distillation percent and temperature of the individual streams. Backblending allows you to define feed streams by blending their associated products. The input products are typically defined in commercial distillations that have a significant overlap across products. Backblending creates an assay from these characterized feed assays by defining data and conditions for their outlet mixture. Backblending creates an assay from these overlapping measurements that can be used as a hysys petroleum refining feed stream. Select the single stream properties option. Selecting the single stream properties option allows you to enter your assay data as a single distillation data curve. You can enter your data on a mass, molar, or volumetric basis. Additional information such as API gravity, sulfur content, light ends, etc., can be entered at a later step. Select the cell currently labeled by mass and change it to the by volume option. Right-click in the left side margin of the distillation data table and select Insert Distillation Percent. Repeat this 2 more times. In this example, samples were taken from a test separator that produced both oil and gas. The produced oil is still assumed to contain some entertained light species, so these must be accounted for when defining the assay. This will be done by specifying an analysis of light ends. In addition to the light ends, the oil assay will also include a volume-based distillation data curve, and API gravity, and average sulfur content. Separate analysis of the gas product from the test separator is also available. This gas analysis will be defined when you enter the simulation environment. This gas material stream will be recombined with the material stream representing the oil assay to represent the composite hydrocarbon mixture. Enter the distillation volume percent and temperature as seen in the following table. Click OK. Go to the Input Summary tab. Double-click on the Center Liquid Density menu item. This allows you to change the default units from the property. Select API at the unit and then click the green check mark to save the change. Enter an API gravity of 17 for the whole crude. In the next row down, enter a sulfur by weight percent of 2.715%. Click the Pure Component tab. You can use this tab to supply light ends data. Double-click the first empty cell in the first empty row. Filter the search selecting C5 paraffin in the component group. Select the component ibutan. Click the green check mark to save the change. Repeat to add normal butane as well. Change the basis percent to by volume and specify the following component percentages for the light end. In the bottom right corner of the Input Assay window, click the Characterize Assay button. Wait a moment for the assay to fully compute. Now the assay is fully computed. You can view the results from the characterization by viewing the Results Summary tab. The table lists petroleum properties for the whole crude. From the Assay Management ribbon tab, you can quickly generate plots of your characterized assay from the plot gallery. Recall that hysys Assay Management tool also generates a fluid package and the component list as the assay is defined. In the navigation pane, expand the component list folder and select component list 1. Note that the standard data bank and the hypothetic components have been used. Now check fluid packages. The property package bank person has been defined. Assay data supplied via the Assay Management tool can be exported for use in other hysys simulations, much like a fluid package. Click Petroleum Assay. Select the Define Assay. Then click Export. Choose a name and file destination. Task 2. Attach the assay. After characterizing an assay and verifying that its associated fluid package is complete, the assay is ready for use in a flowsheet. The step of association the assay data with a material stream is done in the hysys simulation environment. Add a new material stream. Change its name to raw crude. Click on Petroleum Assay. Select Attach Existing. From the pull-down menu, select Assay 1. You can see now that the assay is attached. Select the Composition menu and verify that composition is defined. You can see both data bank components and hypothetical components. This overall composition was generated based on the data provided in the properties environment. Go back to the Conditions page. Set a temperature of 66.5 and a pressure of 3,447 and finally a flow rate of 37 kilogram mole per hour. Now to our third task. Build the flow sheet. Add another material stream to represent the gas portion of the production flow. Change its name to crude gas. Set a temperature of 66 and molar flow of 49.9. Enter the following composition. Add a mixer. Set the error stream to crude gas and drag root and name the outstream. Click on the parameter tab. Set the automatic pressure assignment to the equalize all option. Please note that setting the mixer pressure assignment to equalize all allows you to keep the crude gas stream pressure unspecified. If the pressures are equalized around the mixer, they are all forced to the pressure you provided in the drag root. Add a valve. Change its name to choke. Set the in-stream to well and name the outstream. Please note that no pressure drop should be supplied for the valve. This flow sheet will utilize the hysys bidirectional calculation engine to back calculate the pressure drop based upon a downstream defined pressure. Add a three-phase separator. Set the L stream to manifold. Name the vapor outlet. And name the light liquid outlet. And name the heavy liquid outlet. View the worksheet tab for the high pressure separator property view. Enter pressure of 2068 kilopascal for the high pressure gas stream. This should back calculate your model up to the choke valve. You can see now that the pressure drop across the choke valve has been calculated. Add a cooler. Change its name to Joel Thomson cooler. Set the outlet stream to high pressure gas. Set the outlet stream to cool gas. Name the energy stream. On parameter page, set the delta B to 69 kilopascal. And on worksheet tab, set the temperature of the cool gas to 26.67. Add another valve. Change its name to Joel Thomson valve. Set the L stream to cool gas and name the outlet stream. As with the previous valve, no pressure drop need to be supplied, as it will be back calculated via a defined downstream pressure. Add two-phase separator. Change its name to Joel Thomson separator. Set the L stream to Joel Thomson feet. Name the outstream. On the worksheet tab, set the pressure of Joule-Thomson gas stream to 1724 kilopascal. You can see that the pressure drop across the Joule-Thomson valve has been calculated. Let's arrange our flow sheet and move to the fourth task, add a spreadsheet operation. The purpose of the spreadsheet is to calculate the gas-oil ratio of the production fluid. Add a spreadsheet from the model plate. Enter the spreadsheet tab. Right-click on cell E1 and click Add Import Variables. Choose High Pressure Gas Stream and select Standard Gas Flow variable. Right-click on cell E2, Add Import Variables, select High Pressure Liquid Stream, and select the Standard Ideal Liquid Volume Flow. Right-click on cell A6 and import pressure variable for high pressure gas stream. In cell A4, enter the formula 1 million by E1 over E2. Please note that the formula used in this gas-oil ratio calculation example requires you to use English imperial units. The spreadsheet can support a unique unit set different from the remainder of your simulation. Open the parameters page, change the unit set to field. Return to the spreadsheet tab and fill in column B with some appropriate labels. You can use this spreadsheet to recalculate the gas-oil ratio at different pressures. Now to our final task, run a case study. The case study allows you to monitor the steady-state response of key process variables to other changes in your process. It contains built-in reporting tools to easily present your results in tabular or graphical format. Click the Case Studies button. Add a new case study. In the Independent Variables section, click Find Variables. Select the pressure variable of the high pressure gas. In the Dependent Variables section, click Find Variables. Select the standard ideal liquid volume flow of the high pressure liquid stream. Add also the mass density of the high pressure liquid stream. In the Case Study Setup tab, you can define the calculation states of your independent variable you wish to manipulate. In this case, high pressure gas pressure is an independent variable and it will be evaluated over a range. Set the start range to 300 psi. And set the end to 500 psi. Set the step size to 50 psi. Make sure that the case study type is set to nested. Now your case study is ready to run. Click Run. Go to the Results tab to show the results. These results are shown in tabular format. You have the option to show them in plot format. This concludes our video. See you in the next video.